Electrochemistry is the chemistry that describes how spontaneous chemical reactions are used for the production of electricity, and how electricity can be used to produce non-spontaneous chemical reactions to make it happen. In other words, it describes the transfer of electrons in chemical processes. That means it describes the transfer of electrons in these chemical processes. That means electrons are being transferred from one species to another. The donation and uptake of these electrons are usually written in two separate reactions, the reduction reaction and the oxidation reaction. The electrons are taken up in the reduction reaction by the oxidizer, and vice versa. The electrons are being donated in the oxidation reaction by the reductor. These two separated reactions suggest that we must be able to use the electrons to do work for us, but this does not happen automatically. We have to do something to allow that, which we'll be showing with the following example. Imagine you have a zinc plate that you disperse in a solution of copper sulfate, a typical blue solution due to dissolve copper ions, and see what happens. Almost immediately after dispersing the zinc plate in the copper sulfate solution, a reaction takes place between the zinc metal and the copper ions in solution. Zinc donates electrons to copper ions, the copper to plus ions, which after accepting them will deposit as copper metal on the zinc plate. Since copper has a reddish appearance, it is easy to see and to follow the reaction, and as long as there is zinc available, copper ions will be consumed. Zinc ions do not have a color, and thus during time the solution becomes colorless, meaning all the copper ions are consumed. So here the zinc ions are the reductors and the copper ions are the oxidizers. This reaction is spontaneous because copper is more noble than zinc. But how can we make use of the electrons that are being transferred, as we would like to use them for doing work? It was Alessandro Volta who created that for the very first time with his famous Volta spiral, and it was John Frederick Daniell who realized that it is necessary to split up the reduction and oxidation reactions, which led to the design of his famous Daniell cell. The Daniell cell is best understood by fully splitting the reactions. In that situation, we place the zinc plate in a solution of zinc ions, here a zinc sulfate solution, and a copper plate in a copper sulfate solution in separate compartments. To allow electrons to go from the zinc plate to the copper sulfate solution, a metal wire has been connected from the zinc to the copper plate. Now the copper is being deposited on the copper plate, which results in the solution that loses positive charged ions. This unbalance in charge needs to be compensated by replenishing that compartment with positive ions or removal of negative ions. These ions come from what is called a salt bridge, and it turns out that such a salt bridge is key for operation of an electrochemical cell, such as a battery. Taking this split into compartments into account, we now can also split the two reactions. Therefore, we now write the oxidation reaction and reduction reaction in separate equations. The separation between the metal plate and solution is called the phase boundary and is indicated by a small vertical line. The salt bridge on its turn is then assigned by a double vertical line. With this information, we can write the full cell diagram in a well-defined order, where in the spontaneous reactions the electrons move from left to right, such from the negative electrode to the positive electrode. Notice that at the cathode the reduction takes place, and at the anode the oxidation. You can remember this by Croatia, cathode reduction, and oxidation, anode. If we now block the electron current, the reactions will not take place. This will lead to a measurable voltage, that is a measure of the driving force for a reaction. This voltage is in standard condition 1.1 volt. If we would like use another metal at one of the electrode compartments, the voltage will change. To figure out what the voltage will be, we need to find out the various driving forces for reactions. These values are measured against a standard and tabulated as such. This standard is a standard hydrogen electrode, SHE. This standard hydrogen electrode consists of a solution of 1 molar H+ ions, and so at the pH of 0. In this solution, a platinum plate is dispersed along with hydrogen gas that flows with a pressure of 1 atmosphere. This potential of this reference electrode is set to 0 volt, assigned as capital E with a plimsoll, but usually today with a subscript 0. Note that the idea of using a plimsoll line as a reference comes from the maritime sector, where it is used as a reference mark located on the ship's hull, indicating the maximum depth to which the vessel may be safely immersed when loaded with cargo. With this reference, we now can compare, relate, etc. the various reduction reactions. This is done in the standard reduction potential table. Here the reactions are listed to accept electrons, therefore it's called standard reduction potentials. The higher the reduction potential, the more likely the reduction reaction is, and vice versa for the oxidation reaction. With this table, we now can figure out whether a reaction can take place and what the measured voltage will be under standard conditions. That is 1 molar of the dissolved species and 1 atmosphere of the gases that may be present in the reaction.